So I hope everybody's enjoying their snow day. This is the first video, and I'm going to cover the types of substitution effects and how they affect the electrophilic aromatic substitution reaction. So to refresh your memory on the electrophilic aromatic substitution reaction, I have an aromatic ring which reacts with some electrophile, a really good electrophile, and what we have is the electrons from this ring attacking that electrophile to give me the positively charged intermediate here. All right. So after addition of that, then I can get elimination of the hydrogen from the ring to re-aromatize, and that gives me the electrophilic aromatic substitution product over here. All right, so what if I actually start with a group already on that aromatic ring? Let's say we had some R group attached to this. How does the nature of this R group affect the electrophilic aromatic substitution reaction? We're going to talk about substitution, where that is going to go at first. Right now, I just want to talk how it affects the reaction itself. Okay, so a lot of this work was done. If we take our benzene as our example and set that reactivity, how fast it's going to react, equal to 1, I could see there, depending on what I have on it, I get some different effects. So if I have a nitro group attached to this aromatic ring, I could see it slows my rate down a whole lot. The chlorine also slows down the rate when we compare it to benzene, which is set at 1. And if I put a hydroxyl group on it, I get a dramatic increase in the reactivity, and it reacts 1,000 times faster than benzene itself. So what we're going to do is we're going to go over the nature of all these effects. Most of them are electronic effects. We're going to talk about the inductive effect, what it is, the resonance effect, what it is, and whether that makes the group on the aromatic ring an electron withdrawing group or an electron donating group. Okay, so the inductive effect really has to do with the electronegativities. We're talking about a polar bond, and remember, if I look at something like a halogen, remember back to your general chemistry, if I'm talking about a polar bond, I would get a dipole for this in the direction of the halogen. That would create a positive side, partial positive side on the carbon, and a partial negative sign on the chlorine. And depending on what that group is, remember the carbonyl has a positive charge at this carbon. So the electrons, if this is positively charged, this carbon, because of the dipole that's present in the carbonyl, I'm going to get an electron deficiency here, right? The electrons from this ring are going to try to satisfy that positive charge. And again, I can do the same thing with some other groups that are known as electron withdrawing groups. I'm going to get a partial positive side here. The electrons are going to want to go to satisfy that instead of being able to react. And again, a nitro group is another example of an inductive effect. I also have, for completion, the inductive effect with the hydroxyl group present. This is actually going to be a very, very small effect and is going to be negligible for the hydroxyl group, but I have it here for completion of it. And we see the opposite. If I have an alkyl group, a methyl group in this case shown on the aromatic ring, inductively that's a reversal. I have these electrons that are in this carbon-carbon bond going towards the aromatic ring, pumping electron density into the ring, making it a little more reactive, as we'll see. The other major effect is the resonance effect. If you're rusty on your resonance and what resonance is, I suggest you go back to, I think it's chapter 2 in this book, and play with that. Make sure you understand what resonance is. Remember, in a resonance structure, the only thing we're moving is pi electrons, right? So pi electrons can move around, and you could see that here in this first example. I have the pi electrons coming out of the ring to satisfy and put the negative charge on the more electronegative atom over here, and that resonance structure would be this. So I didn't change the connectivity. I still have carbon connected to Y, connected to Z, just where those electrons are. I've changed where that was. So what that does is that creates a deficiency of electrons in here. So if the aromatic ring is deficient, it's going to be a lot less reaction if the ring is positively charged in this case. And again, I could show this resonance effect where I go to satisfy any positive charge by taking electrons out of the ring and putting those electrons on the more electronegative atom. I create these resonance structures that have the positive charge residing in the ring itself. Okay, with the halogen, even though inductively it's an electron withdrawing group, it could still donate electrons into the ring. And again, when we get to the substitution, we'll go into a lot more detail about this halogen. It's actually both. Inductively, it withdraws electrons out of the ring, but through resonance, it could add electrons into the ring and make the ring more electronegative. Right? So if I look at this, remember I said the inductive effect in the hydroxyl is much smaller because that hydroxyl group can donate its electrons dramatically, making this ring itself more negatively charged and therefore more reactive. In this case, again, we could see that if I do the resonance structures and move this around, I can get that negative charge to be on the para position as well, and I could also move those electrons again and make them on the other ortho position. So both ortho positions are electronegative as well as the para position. Okay, and again we could see here in reference to the reactivity what that does to the ring. So if my group that I have on that ring, this Y group in this case, is electron withdrawing, that's sucking electron density out of the ring and forming a positive charge on that ring is not that favorable. So we're going to get less reactivity and a less stable situation when we compare it to the reactivity of benzene itself, where there's no substituent on that ring other than the hydrogen. If I look at that group Y as an electron donating group, the intermediate of the electrophilic aromatic substitution again has that positive charge, and if I can donate those electrons in, that helps to stabilize this intermediate, and that's going to make it much more reactive towards it. Stability is good, instability is bad, and we can see that stabilization effect in the reactivity of the aromatic rings. So just to recap really quick, if I have an electron withdrawing group attached to it, what that's going to do is that's going to decrease the reactivity of the ring. I'm withdrawing electron density out of the aromatic ring, making it less able to attack that positive E+. And if I have an electron donating group on it, that's going to increase the reactivity of the ring because I'm donating electron density into the ring, making it more reactive. Those electrons are more available to do the attack of that E+ in the electrophilic aromatic substitution reaction.